you're a detective staring at a cluttered evidence board. You've just found two separate receipts proving your suspect was at the scene. Having both receipts doesn't actually give you any new information. It doesn't solve the mystery twice as fast. It just takes up space on your desk and clutters your investigation. In machine learning, we run into this exact same problem when we feed a model overlapping data. It's a phenomenon called multicollinearity. If you evaluate a model suffering from multicollinearity strictly by its final predictions, it might look flawless. It's highly accurate. But if you scrutinize the individual coefficients, you'll find absolute chaos, with numbers swinging wildly in different directions. Curious, how can a mathematical model output such reliable, pinpoint predictions on the outside, while its internal logic is completely unstable? When you have overlapping information, you create a crisis of trust. You can no longer tell which variables are actually driving the decisions, which makes it incredibly risky to trust the model in the real world. To understand why this happens, we have to look at how a model maps out its universe, which we call its vector space. Every independent feature you give a model is supposed to add a uniquely new angle of information. Look at this 3D space. When you have two distinct independent features, they shoot out as perpendicular vectors. Together, they weave a wide, robust, and stable flat plane for the model to build its logic on. But watch what happens when you introduce two highly correlated features that feed the model the exact same information. Those perpendicular vectors swing toward each other until they nearly overlap. Pointing in the same direction, they fail to create a wide, stable foundation. Instead, the mathematics experience a dimension drop. The wide surface area we built physically collapses down into a single fragile line. Because of this structural collapse, the model loses the geometric space required to tell those two inputs apart. Feeding a model more data points doesn't automatically give it more information. Without independence, redundant data just destroys the geometric stability of the system. In linear algebra, a model is always trying to do one simple thing: find the mathematically closest path, or linear projection, to the target prediction point. As this diagram shows, we have a single prediction target. But because our two correlated features are now pointing to the exact same location, the model suddenly has infinite ways to balance their weights to reach that dot. The math just starts guessing. It might lock into a massive positive weight of plus 1,000 for the first feature and an extreme negative weight of minus 999 for the second. The net result is exactly 1, so the prediction looks fine on the surface. But this balancing act makes the coefficients hypersensitive. A microscopic change in the training data can cause those massive weights to completely invert overnight. Multicollinearity acts as a mathematical illusion. It masks a broken, highly arbitrary foundation underneath a facade of accurate predictions. This is why you can never blindly trust a model just because its outputs look correct, and why skipping exploratory data analysis is so dangerous. Take a look at this correlation matrix. It's a diagnostic tool that scans raw data across a grid. When the intersection of two variables lights up dark red, that's your early warning sign that you have secret redundancies hiding in your dataset. To get even more precise, data scientists use a metric called the Variance Inflation Factor, or VIF. It acts as a mathematical radar, quantifying exactly how much a variable's coefficient is being artificially inflated by overlapping data. When you see a high VIF score, you have to make a hard choice. You have to step in and physically remove one of those overlapping variables from the model entirely. It hurts to throw away data, but isolation is required for clarity. You can only understand how a complex system truly works when you hold everything else constant and observe one distinct variable at a time. A model's integrity relies on distinct, independent voices to tell a structurally sound and coherent story.